Hello, everyone. Welcome back to this week's algebraic graph theory seminar. And first, I want to make an announcement. That is, there will be no algebraic graph theory seminar next Monday because next Monday is family days. So we have decided to take a break. And now let's get into today's talk. Next week, we have Tino to tell us about the reverse mixing in quantum walks.
Thanks, Tina. So before I begin, I'd like to really thank you, the organizer. So thank Tina, Sabrina, Sophia, Max, and Maria for organizing these seminars. And I'd like to mention that it's joint work with Ada, Chris, and Sam. So also thanks for coming. And I'd like to make this talk a little bit more interactive. So if you have any questions, please ask me, stop me at any point. I don't have to go through everything I've planned to do actually. So yeah, so we can take it easier. Okay, so I will try to do a board talk. So let's start. So so we have a graph. G, and we assume it's connected. So please let me know if you cannot read the writing. And to be safe, we'll stick with undirected graphs. Okay. And let's assume the adjacency matrix. The graph is A. And let's say the spectral decomposition of this matrix is given as follows. And we'd like to assume this matrix is normalized. So what that means is the eigenvalues are trapped in 1 and 0, between 1 and 0. And we also want to assume that, okay, because it's connected, this is going to be a simple eigenvalue. And let's say fix for the notation that the Perron eigenvector here, the principal eigenvector is Z1. So in particular, we can just assume E1 to be Z1, Z1 transpose here. Yep. Okay, so next thing is I'd like to pick a vertex in this graph. Okay. And actually, I have to use G here, just a vertex here. And we will denote, we'll look at the characteristic vector as vertex. So without loss of generality, let me just assume it's sitting in the first component there. Okay, so it's known classically, if you do a classical random walk, say you do a lazy random walk, for example, that if you start anywhere, you will essentially converge to Z1 if you normalize this properly. So this is essentially mixing. So what we'd like to ask is if we can reverse this process. So we'd like to actually go back to this unit vector. If we allow a quantum walk here. In particular, continuous time quantum walk. So, so that means we'd like to do something like this. Okay. But this is, of course, not possible because Z1 is an eigenvector. So it's easy to see that this one will just stay up to some phase. Yeah. Yeah. So this is not possible. But so the specific question we would like to ask is, what if we were to add rank 1 perturbation to this? So this problem here. So can we go from the principal eigenvector doing a quantum walk on this rank 1 perturbed matrix? In a sense, we are adding a self loop. So if this is the graph, here's the vertex W. We are adding actually a self loop to this vertex W. And we're asking if we were to start in the principal eigenvector, so the steady state, if you like, can we actually send this across back to W? So we want this to be proportional to W. Yep. So this is, in a sense, the reverse mixing that's mentioned in the title. Okay. Is this okay, more or less? Any questions? So this is essentially the goal, to understand whenever this is possible. So let's do an example. So the canonical example for state transfer is K2. So let's actually pick here Kn. And this is a case analyzed by Fari and Goodman in '98. Yeah. Okay, so we were asking, what we're doing here is, what if you have a complete graph here, and we add a self loop, weight 1 to one of the vertices? Can we actually move from the all one vector, which is the principal eigenvector of the complete graph, to this unit vector here? Okay, so let's so the motivation for this is, let me back up a little bit, and I'll come back to this. The motivation, this is actually Grover's search in continuous time. So Grover's search is known to be actually equivalent to a discrete time quantum walk on the complete graph. So what I like to show you here is the formulation by Fari and Goodman that views Grover search in continuous time. Okay. So here's the example. Okay, so I've picked the complete graph, the principal eigenvector. So let's say normalized. It looks like this. It's all one. And if we take the outer product of this, this is essentially the all one matrix normalized by 1 over n. So I will cheat a little bit and pretend this is actually the adjacency matrix of the complete graph. This is not correct because the diagonals are filled in. Okay, but it's just a shift by the identity matrix. Okay, and what we'd like to analyze is actually this matrix, the rank 1 perturbed matrix. This is the complete graph in a sense, with the self loop put on the vertex W. So we are asking whether we can actually send this quantum walk with this rank 1 perturbed matrix from Z1 and then arrive at the unit vector corresponding to vertex W. So this is the question. Okay, so the analysis is simpler if we actually find the right basis here. So let's say this is the unit vector for W, and so also I should define this quantity first. So let's take the projection of Z1 on this unit vector, and this is clearly 1 over root n. So the shadow of Z1 on this unit vector is very small. So let me draw Z1 here. So let's say the projection is here, and let's call this epsilon. And I'm going to take a vector that is orthogonal to EW here, that span essentially where Z1 is spanned by these two vectors. So I need this to be orthogonal. And I would like Z1 to be in the span of these two. Okay. And as such, you can see that written this basis, Z1 is actually something that looks like epsilon 1 over 1 minus epsilon square. If we are writing this in this basis where this is corresponding to the vertex W, and this is the other orthogonal guy. Okay. So because of this matrix here that we're interested in, this matrix here, becomes, so it's right here. So we're going to play this game in this two-dimensional space. This matrix is going to look like, so 1 plus epsilon square, epsilon square, epsilon square. This is 1 plus epsilon square. And then we can, of course, find the eigenvalues and eigenvectors of this. And it turned out that the eigenvalues of this matrix is 1 plus minus epsilon. And the eigenvectors, actually, it's not relevant, but it's stated here, is the corresponding eigenvectors are something like this. So I'm going to match up the plus minus here with the plus minus here. So something like this. But this we can work this up very easily. Yeah. Okay, but the point is if you then ask, okay, so what's happening in this two-dimensional space when we do this? So this is the perturbed quantum walk starting at Z1. The expression that we'll get up to phase is looking like this, minus I sine epsilon t plus, so again, this is just some calculation that can be done. And, yeah. And the goal is we want to send this, to W. So W in this basis is just the first unit vector. So we want to send it to this. And the question is there a time such that this will happen? So can somebody help me specify the time that will work here? What is a good time to pick so that we do reach this 1, 0 unit vector? What would be a good time? So okay, I think the thing to do here is to just blank the cosine, right? So the cosine is 0 if it's epsilon t is pi over 2, for example. So so you can see that by choosing pi over 2 epsilon, this will do the trick. Okay. So this will equal. So this means, yes, we can actually, over a complete graph, if we pick time that is something like the inverse of epsilon 1, epsilon, so excuse me. So the time to reverse this mixing is about 1 over epsilon, which is 1 over root n. So the time is about root n. And that is the time for Grover search, essentially. Okay, so this is Grover search in continuous time. So let me move on to, so because of this example, you can ask us for something a little bit more general. Right? Let's propose the following definition. So let's say a graph family. So now I have a sequence of graphs. So for example, the complete graphs is a sequence of graphs, actually, a family of graphs. So it's similar. So let's say a graph family is gamma. So allow me to just use this term for a stock Grover-like or Groverian. If for all vertex in this graph, so that if you look at the projection, okay, so like before, so I need to assume this is connected, of course, and undirected. Okay, so this is non-zero. Like to assume this is non-zero. So there is a non-trivial projection, and we also need to assume actually this tends to zero. So as n goes to infinity. Okay, and we'll see what. We'd like to impose that the quantum walk scaled, so we scale the adjacency matrix by gamma, and we add the rank 1 perturbation as before, and we were to start from the principal eigenvector of this adjacency matrix of this graph. Then this expression, which is essentially the fidelity, is at least a constant. So let me just use this notation here. So this simply means at least a constant. With a time that scales like cosine t that scales proportionally with this epsilon. And I think for the remaining part of this, just so that I don't get mixed up, let me call this epsilon 1 actually. Okay, the time should scale this way. Okay, so up to constant factors of 1 over epsilon 1. Okay, so this expression here we can call the fidelity. So this is the fidelity of the quantum walk. So we can call this the fidelity function at time t. Okay. Any questions? That'll be okay. Okay. So I'd like to point out this condition here is the quantum speed up condition here. This is the quantum speed up, much like Grover search. So the reason being, the classical bound, the classical time bound is going to scale like epsilon 1 square. So, because the probability of catching W if we sample according to Z1 is the square of those entries, the projection. So this is really the requirement of the quantum speedup. Another quick comment is that this is the optimal time. So so this time requirement here is optimal if it can be achieved. since there is a matching lower bound. There exists a matching lower bound on time. That is exactly that expression. So in a sense, no quantum walk can have time lower than this bound. So if this is achievable, this is optimal. Okay, good. Right. So let me mention more examples that's known. More examples. Actually, sorry, allow me to go back. I forgot to mention something here. This nice example. And point out this. Okay, so I'd like to stress what's happening here for the cliques. So what's happening here, and this is what we are going to chase in the remaining portion of the talk. So if you look at the eigenvalues of this A, it's normalized between 0 and 1. So let's put it here. And after perturbation, the eigenvalue shifted by epsilon. So one eigenvalue move, well, not move, but the largest perturbed eigenvalue becomes 1 plus epsilon. The second largest perturbed eigenvalue is 1 minus epsilon. So there is this spacing between the old principal eigenvalue after perturbation. So there is this gap epsilon here, and there's this gap epsilon here. Okay, so I'll come back to this sort of picture, because what I like to show you later or soon is that this gap here, the gap between the first perturbed eigenvalue to the gap between the old principal eigenvalue must be epsilon for spatial search, well, for reverse mixing to work. Okay, so this gap here is necessary, and that's something I would like to show the remaining part of the talk. So a necessary condition for a graph to be this gamma Groverian is that gap has to be proportional to epsilon 1. Okay. But okay, so let me mention some examples that's known in the literature. Okay, so what we've shown, so Fari and Goodman showed cliques are Groverian. Charles and Goldstone notice the cubes are also. So this is Groverian graphs. So cliques are okay. The n cubes are okay. The hundred cubes are okay. There is also an observation by Jan-Mark, Meyer, and Wong, 2014. Strongly regular graphs are okay. There is some results by Tom Wong and Tanaka Sabri in Portugal just last year. Johnson graphs are also okay. So these are sort of your known examples of graphs that satisfy that condition. So there's also much work done to understand essentially the sufficient and necessary conditions for these graphs to satisfy this property. There is a nice recent result by Chakraborty, Nova, and Roland that showed some nice sufficient conditions for this property. A special case of this of their condition is that the graph has to have a constant spectral gap. But they develop actually something that is actually weaker than this condition. Okay. What I'd like to explore in this talk is actually this side of the this set of conditions, the necessary part. So I'd like to show in what remains of the talk is that if we define this quantity delta plus to be the gap between these two eigenvalues. So so this is the largest perturbed eigenvalue, and this is the largest original eigenvalue. So under this rank 1 perturbation, there is a shift in in the eigenvalue, and let's call delta plus to be the shift. The condition that I'd like to show you is that this delta plus must be proportional asymptotically to epsilon 1. So this picture that we have for the clique, this orange cap is necessary. Unfortunately, we can't prove the same for the other side, this piece here, but we can prove that that the gap is necessary for the largest two eigenvalues. Okay. Any questions before I move to the to show the proof? So looking at this list of graphs, I think for this crowd, I think there are some obvious questions to ask. Maybe we can discuss this later at the end, but the family of graphs that satisfy this property, there's some obvious questions that can be asked for those. Okay. If there are no questions, I think I will try to show you the proof of that necessary condition. Okay, so this is the condition I'd like to show, the claim I'd like to show. So if a graph, so it's actually a family of graphs because the parameter n is actually running in the background. So if this graph satisfies that property, gamma version, then the shift or the gap between the two largest eigenvalues after the rank 1 perturbation must always be proportional to that quantity epsilon 1. So remember epsilon 1. So there is a vertex that's in play here. Epsilon 1 is the shadow of that vertex on the principal eigenvector, and the parameter delta plus is governed by the choice of gamma. Yeah. But essentially this condition has to, so these two parameters have to collude in this way so that this actually is the necessary condition. Okay. So in a sense, this is a little bit strange because when we were looking at this, it didn't seem like this should be necessary, or yeah, because the condition on delta minus is not necessary yet, or we can't prove it. Okay, so let's see this. Okay, so let me write the perturbed matrix as follows. Okay. And let me simplify this notation because let me write this by abuse of notation. Let me just write this WW transpose. So to mean this is actually the characteristic vector of W. And the reason is because the results actually work for any vector, not just these characteristic vectors. Yeah. Okay, and let's assume the spectral decomposition of this perturbed matrix is given as follows. And recall that we had assumed the spectral decomposition of the underlying adjacency matrix is as follows. Okay. And it's normalized. Okay, so I'll remind us during the proof here. Okay, so from here, what we can do is we can multiply by one of these eigenprojectors. So if I multiply by one of these eigenprojectors from both sides, on this side I will simply get this. Is this okay? Any questions? So maybe I should mention here, this is the spectral decomposition. Of the perturbed matrix. Okay, so this is fine, I think. I can combine these. So I'll collect them on the other side. Okay, and and I can multiply by W from the right and collect the constants. Please stop me if something is not clear. So I'm just chasing down the equations actually. Okay, so now I will collect some facts from this derivation. So the first fact is if this matrix is invertible, we can say something more. So I can write this. Yeah. So I can write this. If this lambda p is not in the spectrum of gamma A, okay, then this matrix is invertible. And also because of this dangerous division by zero, let's assume this next to it. But actually, this condition here actually implies this by Cauchy, while interlacing. Okay, this can be proved using the while interlacing. Okay, so but the thing that we would like to read out from here, once you have this, is that 1 equals this. Oh, sorry. So I missed. So I need this one. And here I will get something like this. Okay. Is this okay? So I'm just multiplying this equation here by itself, and then just collect the terms using the spectral decomposition of A, essentially. So at least, so here we get this equality. That's going to be useful later. So let me collect another one. So the second thing we can say is if we were to start from here, and let's multiply through by E1. So I should get something like this. So this is just a constant multiplied through by E1. And they just turn this into constants. And then I get this. Remember the E1 corresponds to eigenvalue 1 for A. So that's why it's done. Okay. And the conclusion here is, again, so I need some condition, but I need to express this expression here as this constant E1W over this difference. And this is only kosher if gamma, I need gamma not to be in the spectrum of the perturbed matrix. So then I'm not dividing by 0. Okay. Okay. So armed with those two equalities, so I will come back and use these two equalities here. So this one and this one. So now let's look exactly at what we need. So let's look at the fidelity of the quantum walk, the quantum walk. Okay. Right. So what I'll do is I'll adopt. It's not necessary, but I think it's also cleaner, the viewpoint of the density matrix. So the initial state that we are moving is actually Z1. So so this, remember, this is Z1 transpose. So the evolution of the density matrix is actually going to look like this. Okay. So this is essentially the density matrix at time t. If we have this initial, so this is the initial density matrix. Okay. And this is at time t. And we are asking the fidelity of this density matrix in relation to the vector W, or the unit vector W. So in a sense, I need to take the trace. I need to take the trace of this with this state. So this will give me essentially the fidelity squared, because I'm doing it twice actually from both sides. And I can simplify this further by saying this is actually by the trace property. I can just do the following. Okay. So this is the expression we need to analyze. Okay, so let me start a different page. So we need to analyze this quantity here. This better walk. This is the initial density matrix. And this is the W vector. Okay, so then I'll just use the spectral decomposition of a tilde. So recall this is assumed to be these guys. So I can just open this up. So let's work on this. This will just be a double sum of the eigenvalues involved this way, and and then I have the eigenprojectors involved this way, and I have the W transpose W here. Okay, so yeah, this is my expression. So now we can actually write this by doubling the E1, like so. And I think I will need to steal one of those equalities we prove for these expressions looking like that. So right here, we want to collect this equality here and use it. So if I were to do that, I will get something along the lines of, so let me make sure I have this okay. So this, it's going to look like this. So what's nice that's going to happen soon to show you here. So there's some denominators here. That and this. Okay. So I'll get an expression like this. So what's nice about this, you notice, if you notice, these are all constants. And actually, so number one, I can actually send this term here outside, and the double sum actually factored independently. So I actually just get a single sum squared. So I get something like this. So be careful here. So yes. So I get something of this form, and then I get squared here. So the two sort of quantum walks from each side actually factor out nicely. Okay. And okay, so I hope this is okay. So now one observation here. So this is actually a nifty trick that that was present in the work by Chakraborty, Nova, and Roland. So what we do here is set time to be 0. Okay. If time is set to be equal 0 in this equality going down, you see in the first expression here, we just get, so let me write this in blue. So if we set time equals 0 here, what I'm getting on the left hand side, if you like, is just this. Yeah. If we were to set time equals 0 here, what I'm gonna get, the last expression is something like this. So, yeah. So essentially, this shows me that this expression is 1. Moreover, I can just cancel the square. Okay, so one observation here that's interesting is this. If we write down the summation, so let's pull out the first factor here. So this is the largest perturbed eigenvalue. This is the original principal eigenvalue. So this is the denominator is positive. The other denominators are negative. Okay? So that means it's actually negative. P not equal to 1. I forgot the transpose. And then I should switch this way. So this is equivalent to this expression. So they differ in sign. So this term here differ in sign with everybody else in this summation, but they make up 1. Okay. Okay. So now let's go back. So now we're almost there. So let's go back here to this expression here. So I have therefore, so we had this fidelity expression squared. It's equal to this. Expression here. So we're going to use crucially the fact that these two terms are differing in sign, but they make up to 1 actually. Okay, so I'm going to cancel the square here. And recall this is actually epsilon 1 square. So this, after taking the square root, this is just epsilon 1. Okay. And now we'll just hit this with triangle inequality. That removes the exponentials here. The numerator is already positive or non-negative. And then we have absolute values. Okay, by using this property here, we actually can bound the p's, the terms corresponding to p that's not the first one. So with a little bit more work, we actually can show that this is twice the first term. And remember, if I pick the first term here, it's lambda 1 minus gamma. That's something we call delta plus. And everybody else, yeah. So I've introduced this factor of 2 here, but I have to subtract 1 so that to account for this equality here. Okay. So we're just bounding away the terms corresponding to p that's not 1 by using the dominant term here. Okay. And now this is the first observation. So let me clean this up a little bit. So, okay, this is what we have. And now the easy conclusion here is this tends to 0 if epsilon 1 is asymptotically smaller than delta plus. So the fidelity goes to 0, meaning the graph is not Grooverian if this condition is true, because the delta plus term will send essentially in the limit this ratio to 0. And this is bounded by 1 anyways. And this term is already going to 0 by assumption. Okay. Okay, so now we have to complete this this whole thing, we have to reverse this. I want to prove the same thing under the assumption that it goes the other way. Want to show that this is also going to lead to failure. Okay, so for this one, we now will come back and collect the second equality that we just observed. This one. Yes.
You have about like 3 minutes left. So.
Yes, I'm almost done.
Okay,
thanks.
Good.
So yeah, so from here, setting p equals to 1, which is safe for these assumptions, I will get this. So that is the left-hand side. And I will lower bound the sum by just the first term, like so. So p equals 1, r also equals 1. And this is gamma. And remember, this is something we've been calling delta plus. And this essentially gives us a upper bound on this term here. This is something we've, oh, sorry, so I forgot a square here, yes. This is square, this is square, and this is something we've been calling epsilon 1 square. Okay, so we have an upper bound on this term, that is the ratio of these two, and I will use it here. And that will bring us home. So I will use that upper bound here. So remember, from above, I have this. So now plugging in that bound, we actually get the ratio, the fidelity, sorry, is upper bounded by, so just put this here. And I have here, and I have here. So this allows me to cancel one side. and I get this. And this also tends to 0 if delta plus is asymptotically smaller than this. So this essentially says if if the property holds, then the condition we need is that this has to be asymptotically equal to this. And that concludes the proof. Okay, so that may be a bit technical, but okay, so let me, Tina, can I just have a few lines to mention questions, and I'll stop after these questions.
Sure.
Yeah, thanks. Okay, so some obvious questions is being Groverian determined by spectra. Completely determined by spectra. Are there nice necessary conditions for the other side of the gap? And characterizations for the scaling gamma. Okay, so sorry for running over time, but I think that's all I have. Thank you.
Thank you, Tino. So is there any question for Tino? Yes.
Hi, Tino. Thanks for your interesting talk. And I have a simple question that if there's some relation between mixing time and reverse mixing time. I mean, in random walk version and then quantum walk version, like if there's some relation between that.
That's a good question. You mean, is it true if it mixes, classically it mixes at some time, it will get reflected in the quantum walk?
Yes. Yes, like initial vector, starting from initial vector, and then that vector becomes the stationary steady vector, and then the time for that. I mean, that time has to do with reversing mixing time.
Yeah, not that I'm aware of, but that's a nice question. Yeah, not that I'm aware of.
Okay, thank you.
But that's a nice question.